solving techniques.
It sounds like a good argument for having small focused sections within larger courses, especially early on. Yeah. Okay. Thank you. We're going to move on to our next speaker, Victor Odouard, on communication, cooperation, coevolution. You're just trying to shut me up, dude. Communication, cooperation, coevolution, exploring the origins of talk.
Hey, yeah, thanks to everybody who has survived until this point. I know it can be tiring to watch Zoom presentations. Let's see. All right. Can people see? Yes.
Yeah, we can see it.
You can see.
You might want to go to full screen.
All right. Is it black now?
Yes.
Okay. Okay, cool. So today I'm going to talk about communication and cooperation and their possible coevolution. And I want to focus on one aspect of their relationship in particular. And it has kind of a technical name. It's called gossip. And the way this works is, say I do a bad thing, and then you tell everybody, and then I get canceled. And maybe I don't like that. So instead, I do a good thing, and then you tell everybody that, and then everybody likes me. And so you can kind of see how gossip maintains cooperation. But where did the gossip come from? And specifically, where did the communication system that the gossip is built on top of come from? Because communication requires, everybody to agree on what words mean. It requires truthfulness and so on. So it's not just some kind of trivial thing. And today I want to explore the possibility that maybe just as gossip maintains cooperation, maybe there's a circular relationship where cooperation then goes back and maintains the communication system that gossip is built on top of. So the question that I'm dealing with is, can cooperation and communication maintain each other? And the answer is yes, that I found, but terms and conditions apply. And I do want to just go through this question and define the terms more precisely, so then we can build up a model to try to answer the question. So the first word, or the second word in the question, cooperation. What's that? So for our purposes, we'll say that cooperation is paying a private cost, C, for the benefit B of somebody else. So say I'm helping you plant your vegetable garden and I have to invest some time. So that's a cost to me. But then you get the benefit of the vegetables, and hopefully the benefit of the vegetables would be more than the cost that I paid to help you with the planting. So there would be some kind of net benefit to me helping you out. So let's say that B is greater than C, and the benefit's greater than the cost. So if we observe this, we actually see that it creates a prisoner's dilemma, because if you meet a partner and you have to decide whether to cooperate with them, and they have to decide whether to cooperate with you, you get a payoff matrix that looks like this. So if I cooperate and you cooperate, then I get the benefit of cooperating, but I still have to pay the cost. So the payoff is B minus C. If I cooperate and my partner defects, then I have to pay the cost, but I get no benefit. If I defect and my partner cooperates, then I get the benefit without paying any cost. And if we both defect, then we both get nothing. And the problem here is, and this is the trademark of prisoners' dilemmas, is that defecting always gives the best payoff, because no matter what my partner does, if my partner cooperates, well, B is greater than B minus C, so I want to defect. And if my partner defects, well, 0 is more than negative C, so I still want to defect. So no matter what, I want to defect. And so the question is, well, how did we get cooperative societies? And so there are many hypotheses for this. Today, I'm going to focus on indirect reciprocity, because it has to do with communication and gossip. And so the way this works is individuals hear gossip about each other, and they can cooperate with partners who have a reputation for cooperating. So if everybody employs this rule, it creates kind of an incentive to cooperate. So the way this might look is circle meets square, circle cooperates. Then in circle's subsequent interaction with pentagon, square can tell pentagon, hey, circle is good, circle cooperates. And then pentagon will cooperate with circle. So it's a reward for cooperating, and it incentivizes cooperation. But the question here is, where did this communication system come from? And this is important because communication isn't just me saying words to you, because if I tell you a word that you've never heard before, then it's totally meaningless. And so really signals really start off as meaningless tokens. And we want to understand when information actually gets transmitted. And there are two criteria for this. One is uniformity. So individuals agree on what the meanings of symbols are. So for example, say we say 0 means defector, 1 means cooperator, and everybody agrees on that. Well, then that's a uniform communication system. But that's not enough, because we also need the communication system to be separating, that different symbols stand for different situations. So an example of a no-no would be that 0 means both defector and cooperator, because then if I tell you 0, then you still don't know whether you're dealing with a defector or cooperator, so you don't get the information. So that's bad. And so what we're asking when we ask, can cooperation maintain communication? We're asking, well, can cooperation maintain a communication system that has these properties, which are somewhat difficult to achieve? And so to answer this question, we can modify our indirect reciprocity model. So before, what we had was we assumed the communication properties. So we had square interacting with pentagon, and square says circle is good. And so we assume that there's a word good that both square and pentagon agree on, first of all. Also, we assume that there's probably a word bad that square could have used had circle defected, and so on. So here we just assume the communication, but we don't want to assume that anymore because we're asking whether cooperation can maintain the communication. So instead, what we do is we start with communication starting off as meaningless. So square might say circle is 0. And 0 can maybe square says 0 about everybody, defectors and cooperators. Maybe square says 0 about cooperators and 1 about defectors, or maybe it's the other way around. We don't know. But the question is, once uniform and separating communication is attained, does the necessity for cooperation maintain it? So that looks kind of like this. We have communication that maintains cooperation through the process of indirect reciprocity and gossip that I talked about earlier. But then maybe cooperation, the necessity to cooperate, maintains the properties in communication that we desire. So the final component of this question is to understand what maintenance means. And I use the definition of evolutionary stability here. So a behavior is stable, it's being maintained if, when it is the norm, it outperforms alternative behaviors. So for example, cooperation is stable if, in a cooperative world, cooperators outperform defectors. Or going back to Flatland, the square behavior is stable if, when circle shows up, the squares still outperform the circle. The square behavior outperforms the circle behavior. And so in this case, then the squares will outcompete the circles and the squares will remain dominant. So they'll remain a stable state. And so going back to our question, can cooperation and communication maintain each other? We now have the tools to make it a little bit more concrete. So let's say we have the world of squares, and the squares all agree that 0 means defector and 1 means cooperator. So they have a separating and uniform language. And they also have a particular practice for acting, which is they defect with zeros, that is, they defect with defectors, and they cooperate with ones, they cooperate with cooperators. And so if you notice, if everybody starts off cooperating, then everybody will signal 1 about everybody else. And then everybody will continue to cooperate with everybody else. So you get like an entirely cooperative world where everybody also agrees on the communication system, and the communication system is working nicely. So this looks good, but we need to know if it's stable. So for example, if pentagon comes in and pentagon signals 0 about everybody, or triangle comes in and triangle defects with everybody, or circle comes in and circle cooperates with everybody, can any of these strategies do as well as the squares? Because if they can, then the square state is not stable. But if the squares outperform all of them, then the square state is stable. And so the answer is that you can get a stable state with the squares, but first we have to patch up a few instabilities. So the first instability is the irrelevance of language. So say we have square 1, and square 1 meets pentagon, and pentagon cooperates. Then square 1 signals to square 2 that pentagon is a 1. And so the rule with squares is they cooperate with 1, so square 2 will cooperate with pentagon. And this looks like it's working as it should, but you notice that square 1 signals about pentagon's action, And then square 2 acts on square 1's signal, but there's no dependence on pentagon's signal. Pentagon can say whatever pentagon wants about square 1 and will suffer no consequences for saying the wrong thing or the non-conforming thing. And so this leads to problems because if we have the world of squares and pentagon shows up and say pentagon signals 0 about everybody, that's the wrong language, or that's a non-conforming language. But pentagon will do just as well as everybody else because there's no dependence on pentagon's signal. So to fix that, we add a component of, we add what we call meta signaling, which is some interactions have an observer. So that's square 1 in this case. And square 1 is observing an interaction between pentagon and square 2. And say square 2 cooperates. But then pentagon, in an act of defiance, says square 2 is 0. And that's the wrong signal. Squares mark cooperators as 1. And so now square 1 sees this and signals 0 about pentagon to indicate that pentagon has done a socially destructive action or something like that. And so that patches up that instability, but there are more. And the next instability is the unexpressed genes problem. So if we have our world of squares, like I said, everybody is cooperative. And so if circle comes in and circle signals 1 about everybody, circle signals 1 about defectors, 1 about cooperators. There's no, the circle is indistinguishable from all the squares because since there are no defectors, you never get to see how circle will signal in response to a defector. So circle can come in and start doing just as well as the squares. And so to fix this, we add a component of error. So with some small probability, agents will deviate from their prescribed strategy. So square will usually cooperate, but in this case, square by mistake defects, let's say. And then we see that circle will signal square is a 1, which is a non-conforming signal. So in this particular case, now circle's non-conformity can be observed. And so you can see how error actually allows these unexpressed genes to be expressed. And so that fixes our second instability, but there's still one more, and that is the problem of insufficient nuance. So the way this might look is square 1 interacts with pentagon, and triangle. I'm mixing up my shapes now. So triangle is a defector, and so triangle defects. Square 1 says to square 2, triangle is a 0 because he marks defectors as zeros. And so to punish triangle now, square 2 will defect against triangle. But then in the subsequent interaction, now triangle signals to square 3, well, square 2 is a 0, square 2 defected. And so square 3 will now defect against square 2. And so you see what's happening is square 2 is enforcing cooperation by defecting with a defector. But now square 2 loses out for having enforced the cooperation. And so square 2 is getting punished for this actually kind of productive behavior. And so the way we fix this is through this mechanism of nuanced signaling. So signals can distinguish between good defections and bad defections. So if you defect against a defector, well, that's a 1. That's good in the square language. But if you cooperate with a defector, that's bad. If you defect against a cooperator, that's also bad. And if you cooperate with a cooperator, that's good. So you have like a little bit more nuance here, and it allows us to distinguish between selfish defection and punishment defection. And actually, if you make all these 3 fixes, it suffices to create a stable state of like highly cooperative and highly communicative agents. So in conclusion, communication and cooperation can maintain each other. You just need a selection pressure on language. You need error to express these unexpressed genes. And you need a more nuanced signaling scheme that allows a distinction between productive defection and non-productive defection. So big thanks to everybody who watched today, and in particular, Shimon Edelman, who has honestly been such a formative mentor for me in the past 3 years. Thanks so much to you, Shimon. And also Michael Goldstein for his always patient guidance, Michael Macy for his really thoughtful and insightful comments, Jim Finlay for actually guiding me into the College Scholar program in the first place, and Alex Vladimirsky for his help with the math. So thank you all.
All right, Victor, thank you. You know, I think I learned more in the last 13 minutes about this than several books that I've read. So I wish I'd bumped into you first. So thank you for that. So any questions for Victor? Shimon?
I try to give a chance to others, but okay, I'll jump in. Victor, wow, what a talk. Something that we discussed, but I don't remember us reaching a conclusion. How likely is the initial symmetry breaking? I mean, there is no initial settling. There's no given meaning, is zero good or bad to begin with.
Yeah, so that this question, I think, this research was a mathematical model, so it was all just like analyzing stability of a particular state. To figure out the probability of fixation on such a communicative state. So right now I said, okay, so once we achieve this state, is it stable? And then the other question that I think you're asking is, well, how likely are we to get to that state in the first place? And that I would like to explore, and I think I'll use simulation to explore it. So just like start off with, all these agents with like kind of crazy languages, and then see if it converges to a communicative state. Yeah, so that's something that I haven't yet explored, but is like an important follow-up to this.
Michael? Oh, you're muted.
Wonderful presentation, Victor. It's really nice to see how the project has evolved. One question is about invasion. So in order to, another strategy, in order to be able to invade the population doesn't have to outperform, right? It only has to be just as good as the existing strategies. So if assuming that the gossip system is extremely effective and it makes it so that everyone cooperates because you don't want to have a reputation as a non-cooperator, then wouldn't it be the case that you would have, it would become possible to just invade a strategy that unconditionally cooperates could invade because there are no defectors, and that spreads. And so then pretty soon people stop even listening to gossip anymore. They just cooperate. And now a defector can invade.
Yeah, that's the counterintuitive thing, because when you have this world of these what are called discriminators, so those that defect with defectors and cooperate with cooperators, it's actually not vulnerable to invasion from defectors. It's vulnerable to invasion from cooperators because the world becomes cooperative. Yeah. And then these cooperators can come in and they're indistinguishable, right, from these discriminators, until then they make up by drift maybe a larger proportion of the population, and then it's vulnerable to defectors. And so this is fixed by the nuanced signaling that I describe at this normed signaling that I describe at the end. In the literature, it's usually called norms, and so that says cooperating with a defector is bad. And so if you have that kind of norm, then a cooperator that comes in and cooperates with a defector is then defected against. But this, of course, requires there to be defectors. And so in order to distinguish between, in order for the situation to arise, there needs to be defectors. And that condition is satisfied if there is error. So it's like a couple of these of the patches that I added on end up kind of sort of mitigating that specific problem that you raised.
Great, very, very interesting.
Victor, thank you.
I have a question.
Oh, where?
Do you mind?
Daniel, yeah, go for it.
Do you know if this is the unique stable state, or is there perhaps another stable state of, let's say, everyone defecting from everyone also in this same model, or something?
So within the confines of this particular model, I'm sure it's not the unique cooperative communicative state, because you can just say another state is defectors are defectors are, you mark defectors as 1 and cooperators as 0, right? So you just swap the symbols in a kind of trivial way. That's also a stable state by symmetry. But as far as in this model, it's the unique cooperative and communicative state. And as far as it being the unique stable state of the model in its entirety, sorry, aside from it, and so now whether there's a stable state of entirely defectors and stuff like that, I would have to think about that, and I can get back to you. But yeah, it's not the unique cooperative and communicative state, because there's that symmetrical state that's also stable.
This is very interesting.
I'm happy to put you two in the same